So we have the fundamental particles. Quark and leptons are actually categorized as a fundamental particles. So if I make a flow chart of the particles are actually two main classes are there and then subclasses. So we have first the two main classes. One is known as the lepton family. Another one is known as the quark family. The quarks experiencing strong nuclear force interaction can interact with a weak nuclear as well, but mainly strong nuclear, where leptons always experiencing weak nuclear force. The quarks are divided into the combination of the quarks are divided into two categories. We may have three quarks together. We may have two quarks. Like the quarks is not like individual independent quark exists. It can exist as a pair. Like we may have three quarks pairing up. We may have two quarks. When we have three quarks together, what we call these particles, we call them as baryon. And when we have two quarks together, what we call these particles, we call that as meson. So the fundamental particle like electron is there. Then we have electron neutrino. We have tau neutrino, muon neutrino. And their antiparticles are there like a positron, anti-electron neutrino, anti-tau neutrino, anti-muon neutrino. For a quarks, we have up, down, top, bottom, charm, strange. The anti-quarks, anti-up, anti-down, anti-top, anti-bottom, anti-charm, and anti-strange. But as I mentioned, the quarks exist. Usually quarks, independent quarks, you find quarks are existing as a group of particles, like as in a group, and these groups might consist of two quarks or it may consist of three quarks. So if a quark consists of, or a combination consists of three quarks, what we call baryon. Like let's say we have three quarks which are making one particle together, and it consists of up, and down. So what will be the charge of this particle if it consists of up, and down? So up, and down, what is the charge of up? It's a positive degree, so plus 2 by 3. This is also plus 2 by 3. And the down will be minus 1 by 3. What is the total net charge? Plus 2 by 3, plus 2 by 3 and minus 1 by 3. What I will get the net charge? The result? I'll get the net charge is plus 1. The final charge. So we get the plus 1 as the net charge as a combination of three quarks. And what is this particle? This particle is actually a proton. So proton is not a fundamental particle. Proton itself, it consists of three quarks, which is a combination of two up and one down. So up, and down combine together to make a particle which we call proton. And what is the force between these particles interaction? So they, according to a string theory, they have a strong nuclear force between them. So whenever we have a quark, the quark might be a combination of three quarks or it might be a combination of two quarks. If we have three quarks together, we call that as a baryon. So let's say, take an example, we have three quarks in which two of them are up and one is down. So when two up and one down together, when we find the net charge on this, because the up is plus 2 by 3, another up is also plus 2 by 3, and the down is minus 1 by 3. When we take an LCM 3, so it will be plus 2 minus 1. So it will be plus 4 minus 1 by 3. That is plus 3 by 3, which is equals to plus 1. So the net charge on this particle will be plus 1. And what is the particle which is having a plus 1 charge? That is the proton. So actually, proton is not a fundamental particle. It consists of three quarks. Is it clear? This concept of the proton? And proton is also known as a baryon. The term baryon is a term used for the combination of quarks. So three quarks will make a proton. And it's not like the three quarks always result in a formation of a proton. What if we have a different combination? Like let's say this was forming a proton. Let's say another combination is there we have of the three quarks. It is up, down, down. So up, down, down. What will be the net charge on this up, down, down? So up, down and down. So up is plus 2 by 3. Down is minus 1 by 3 and down is also minus 1 by 3. When you take 3 LCM, it will be plus 2 minus 1 minus 1. So it will be 0 by 3 and 0 by 3 means 0. So the net charge will be 0. The baryon which is having a net charge 0, what we call that baryon? We call that as a neutron. Actually, neutron is not the fundamental particle. The neutron actually consists of three quarks in which two of them are down and one is up. So whenever quarks are existing, you will find the combinations, the quarks existing in combinations. So when three quarks are together, what we call this combination, we call them as baryon. So proton and neutrons are actually baryons. Is it clear, the concept of a baryon? Any doubt in this? Okay. Then we have a meson. Meson is another combination. Meson, it's a combination of the two quarks, but the condition is that one should be quark and one should be antiquark. So what will happen when we have two quarks together, we call meson, but it should be quark and antiquark. Like example, if we have up and anti down together, they will make another particle, another group of particle, and that group of particles are called mesons. You have not studied much about the mesons in throughout the course, like in even in IGCSE level or in A levels, you have not studied anything about mesons. So when quarks and it's not like the same anti-quark, it can be anti-quark of anything, but when one quark and one anti-quark combine with each other, they will form a particle which we call a meson. So, and what will the charge on this meson? There is up, so it will be 2 by 3, and there is anti-down. Because down is minus 1 by 3, so anti-down will be plus 1 by 3. So when we take an LCM, so it will be plus 3 over minus, like plus 3 divided by 3. So we got plus 1. So a meson which is having a plus charge, what we call that as a pion. There are different types of meson. So this is a pion or a pi positive. So main thing is the meson is a combination of two quarks, where baryon is a combination of three quarks. And collectively, like together, this meson and a baryon, there's a common name for them. We call them as a hadron. Together, if it's a three quarks or two quarks are there, there's a common term used for them. It is called hadron. So maybe you have heard the name Large Hadron Colliders in CERN. So what they do, what are the Large Hadron Colliders? Actually, they're colliding the baryons and the mesons to identify or to get the basic idea about the structure of an atom in detail. That's why the particle interaction occur at a very high speeds, and they use the hadron colliders so that they can they're trying to break down the quarks into further particle. But till now, the quarks and the leptons are the one which does not further break down. So the smallest particles are the quarks and the lepton. That's why we call them as a fundamental till now. So if you just recall, in grade 7, you have studied like Dalton atomic theory. So Dalton gives the basic structure of an atom, basic structure of a matter's atom, and atoms are indivisible. Then in higher grades, you start to learn that atom is not indivisible. Like atom consists of particles such as proton, neutrons, and electrons. And this, now in this scale, you have learned that the electrons, but this proton and neutron are not fundamental. Actually, they are combination of the quarks. So till now, we are at this level that we consider electron and the quarks are the fundamental or the basic particles. Maybe in future, we may find new particles or group of particles, but till now, and actually a lot of theories support this, like this idea that electron and the quarks are the fundamental particles. So we have the particles. A particles can be a hadron or a lepton. Hadron is actually combination of the quarks. The main here we will have the quarks. This is a combination of the quarks. So it might be a baryon which consists of 3 quarks. It might be a boson which is a quark and antiquark. And examples of hadrons such as protons and neutrons. An example of baryon is a proton and neutron. No, bosons is another thing. Boson is a concept for interaction of the field. Bosons are actually particles which are responsible for interaction of the field. Like example, say there is a proton and there is an electron. They are applying force on each other, or they are in the field of each other. So how they're exerting force on each other? By exchanging a particle in the field, and that particle is called boson. So bosons are actually the field particles, but not the fundamental one. It's just a particle which are responsible for interaction in the field. So a magnet is there. So we have a magnet and we place another magnet. So if there are like poles, they will repel. If there are unlike poles, they will attract each other. So how the two magnets are pulling each other without exchanging, without interacting, like without touching each other. So they exchange a particle. What particle they exchange? That particle is called boson. And what is the boson here? The boson is the photon. Is it clear? The basic particle structure? Why not graviton? Yes, there will be if we talk about, they will have a gravitational field, but the mass of the magnet is very small. The mass is very small, so we can neglect the mass. Like the two magnets are not pulling because of the gravity, they're pulling because of the electromagnetic force between them. And that is why we call this boson will be the photon. If the masses were there, we'll say this boson is a graviton. If the quarks are there, like example, if I have up quark and it is interacting with a down quark, how they exert force on each other? By exchanging a particle we call boson. But what particle is transferred between the quarks? That is called gluon. Gluons are responsible for the strong nuclear force. If it is a weak nuclear, like electrons is interacting with another electron, or leptons are there. So how they are interacting? They are exchanging a particle which is also called boson. But what is the boson of a weak nuclear? These are the WZ boson. If the two charges are there, even like electrons also have charge. So because of interaction of the charge, they will also have a force. And how they are interacting, this force will also be experienced by a boson. But what we call the boson, these bosons, we call them as a photon. The electrons also have a mass. So they're also interacting because of the mass. But it is negligible. So they will exchange a particle which we call boson. And what are the boson of the gravity? We call them as a graviton. So graviton, WZ and photon, 3 bosons are exchanging. But which is major interaction, like which is stronger here, depending, that we'll consider. WZ are the bosons for a weak nuclear force. And for gravitons are the bosons for a gravitational force. Photons are the boson for the electromagnetic force. And gluons are the bosons for the strong nuclear force. So interaction of the particles is by exchanging a particle which we call boson. So bosons are not categorized here because bosons are the field particles. Then we have nuclear decays are there. When a nucleus is unstable, it starts to emit out radiation such as alpha, beta, and gamma. So when a nuclear decay happen or occur, when a atom is unstable, it tend to emit out radiation, and the phenomena is spontaneous and random. This random and spontaneous emission of the radiation is known as the radioactivity. And when it start to emit out these radiation, there are three possibilities. One is it might emit out alpha. One is it might emit out beta. Or it may emit out gamma. Gamma emission is there. Alpha means when a nucleus is unstable, when the radioactive nuclei is unstable, it start to emit out group of particles such as two protons and two neutrons from the unstable nuclei. When two protons and two neutrons are emitted out from the unstable nuclei, we call that as alpha. When an unstable nucleus emitted out either electron or positron, because sometime it emit out electron, sometime it emits out positron. So this is called a negative beta decay and this is called a positive beta decay. And when the nucleus is unstable, it emit out electromagnetic radiation, the radiation to the surrounding due to the vibration or a recoil. As the nucleus vibrate, it emit out electromagnetic radiation. We call that as a gamma emission. What happened in an alpha emission or alpha decay? That if a radioactive nuclei which is unstable like A, X and Z, so when it will emit out alpha, the nucleon number does not nucleon number changes by 4 because the 4 protons and 2 protons and 2 neutrons are going out, and the proton number decreases by 2 because 2 protons are going out. And this is a symbol for alpha. You can also use a helium nuclei like symbol for the helium as well. This is alpha decay. What happened in a beta decay? A positive or a negative beta decay. In a negative beta decay, a neutron will break down into proton and electron, and this electron goes in outside. This is called negative beta decay. But in a positive beta decay, what will happen? A proton break down into positron and neutron. So when a proton break down into a positron and a neutron, it emit out a positive electron, which is also known as a positron. We call that as a positive beta decay. So the equation will be different for a positive and a negative beta decay. Like for a negative beta decay, if we have a radioactive nuclei, when it emit out, the nucleon number does not change. Why? Because one neutron is decreasing, one proton is increasing, so the sum will not change. As a nucleon number is a sum of proton and neutron. So the nucleon number remain unchanged. What happened to the proton number? Because the one proton is increased, so the proton number increases by 1. And this is a symbol for a beta, the electron. But in a positive beta decay, what will happen? A radioactive nuclei, a proton break down into neutron and positron. So the proton number decreases, but the nucleon number remain unchanged. As you can see, and it is emitting, and the proton number decreases by 1 because the proton is break down, And the symbol for a positron, this is a symbol for positron. So in a negative beta decay, what happened? A neutron breaks down into proton and electron. But in a positive beta decay, a proton breaks down into positron and neutron. So that's why when we compare the product, the nucleon number does not change. Nucleon number is the sum of neutron and proton. Neutron number is decreasing, proton number is increasing, but the sum remain unchanged. But this proton remain inside the nucleus, so the proton number increases by 1. Here what will happen? A nucleon number does not change. Why? Because a proton is decreasing and a neutron is increasing. So proton decrease, neutron increase, the sum remain unchanged. But what happened to the number of the proton? The number of the proton have decreased by 1. So that is why it will be Z minus 1. So whenever a negative beta decay happen or occur, the proton number increases by 1. Where the positive beta decay occur, the proton number decreases by 1. And in the gamma emission, there is no change, as it's not emitting out any proton, neutron, or electron. As a result, there is no change in the mass or the proton number. Is it clear, the two beta decays, the positive and the negative? So in a negative beta decay, only a neutron breakdown. In a positive beta decay, proton breakdown. So breakdown of a neutron result in a negative beta decay. Breakdown of a proton result in a positive beta decay. Is it clear? Any doubt in this? So positive beta decay only occur when the proton breakdown. We can also explain this in terms of the atomic level. Like example, let's say take example of a negative beta decay. What happened in a negative beta decay? If I write the equation, complete equation, in a negative beta decay, a neutron breakdown. This is the overall general equation. The nucleon number remains same. The proton number increases by 1 and it emits out electron, sorry, the negative beta decay. When we write in terms of atomic level, so what happened in terms of atomic level, a neutron break down into proton and electron. And there's also another particle, we normally ignore that, but that is there for conservation. There's a particle called electron neutrino, anti-electron neutrino, that is also emitted out during this decay. But when we further break down, what was neutron? Neutron was a baryon. If you recall the structure of a neutron, the neutron is a baryon which include up, down, down. So the neutron is a baryon which include up, down, down. What was a proton? The proton is also a baryon which consists of up, up and down. So up, up and down. And then electron is there. And then anti-electron neutrino. Now if I further simplify this, this up will cancel with up because it is same both sides. Down will cancel with down because it is same both sides. So if I further write a simplified equation, it will be down changes to up gives electron and anti-electron neutrino. If I want to check whether this equation is right or wrong, if I check the conservation of the charge. So if we check the conservation of the charge, what is the charge of down? What is the charge of the down? Down is what? Down is minus 1 by 3. So down is negative degree. What is the charge of up? So it is plus 2 by 3. And what is the charge of electron? It is minus 1. And what is the electron neutrinos does not have a charge, so 0. Is the charge conserved? Is minus 1 by 3 is same as plus 2 by 3 minus 1? Anti-electron neutrino does not have a charge. Electron neutrinos and anti-electron, they don't have a charge. So when I simplify this equation, because you can see plus 2 by 3 minus 1, if you take 3 LCM plus 2 minus 3, so it is minus 1 by 3. So what it shows, it shows minus 1 by 3 same as minus 1 by 3. So means this equation is correct. This interaction is correct. So the charge is conserved. This is an evidence that this is a right equation. So in a atomic level, what happened is actually one of the down quark has converted into up quark. So when the nuclear decay was happening, like when a nucleus was emitting out a negative beta decay, so let's say this is a nucleus. So it was having a neutron. It is having other particle, but it was having a neutron which was up, down, down. What happened to this? It's one of the down changes to up. So when one of the down changes to up, so it will become up, up, down. So it was a neutron, it converted into proton. But that is not the only thing happened. What other thing happened is it's emit out electron and anti-electron neutrino. Electron and anti-electron neutrinos goes out from the nucleus and the proton remain within the nucleus. So this is the overall equation, but this is a atomic level what changes happen or occur. Is it clear? This example of a negative beta decay? What is the purpose of the neutrinos? A neutrino is for conservation of a lepton number. When interaction happen or occur, you're not learning that in detail, but I will give you as an information. When a conservation happen or occur, it's not about the charge. What we do, we check the mass energy conservation. We check the charge conservation. We check the lepton baryon conservation. We check the strangeness conservation, sorry. So these are the conservations we check, but you're only, because it's a basic level, so you'll learn only a charge conservation here. Like you're checking a charge is conserved. But we will check the baryon, we'll check the lepton, strangeness, and the energy mass. These all are checked to give an idea that this reaction will proceed or no. So let's take an example of a positive beta decay. So what happened in a positive beta decay? A positive beta decay, as we just wrote the equation, like an element is there. The nucleon number does not change. The proton number decreases by 1. And this is a positron. And it also gives another particle which is called electron neutrino. So if it's a positron, it will give electron neutrino. That's due to the conservation of the lepton number. But you're not going in detail of the conservation of a lepton number right now. So we'll just consider that it is there. But you will just try to remember when electron is there, it will have anti-electron neutrino. If a positron is there, then it will have electron neutrino interaction for a lepton number conservation. Now, what happened in a positive beta decay? In a positive beta decay, a proton break down into neutron and positron and electron neutrino. So when we check, when we write in terms of the particle, the proton has break down into neutron, a positron, and electron neutrino. If we write them in terms of the fundamental particles, so actually what happened, proton is a baryon, which is not a fundamental, which is consists of the quarks, 3 quarks, which is up, up, and down. A neutron is a combination of up, down, down. This is a fundamental particle, so which cannot break down, same as the electron neutrino. When we simplify this, up cancel with up, down cancel with down. So actually what happened is one of the up quarks has converted into a down quark, a positron, and electron neutrino. Now we check the conservation of the charge. This is 2 by 3 plus 2 by 3. This is minus 1 by 3. This is positron. The positron is opposite of electron, so plus 1. And neutrinos does not have a charge. So when you simplify this, this will be plus 2 by 3 on the right, and it will be plus 2 by 3 on the left. So it means the charge is conserved. So actually what happened in this interaction, that one of the proton, which is a combination of up, and down. So that proton has changed the quark to up, down, down. And as a result, it also emit out positron and the electron neutrinos. So this is a neutron and this is a proton. This is what happened in an atomic scale whenever a positive beta decay happen or occur. Is it clear? Any doubt in this? Okay. What if the charge is not balanced? Then it means this conservation, this is not possible. Like this interaction will not occur. This, like, if, let's say I wrote an equation, I wrote proton, a proton has turned into another proton and a neutron and electron, neutrino and electron or a positron. And I want to find whether my equation which I wrote is right or wrong. So I will check the conservation of the charge. Even I can check the conservation of the charge without breakdown, because I know proton is plus 1. This is also plus 1. This is 0. This is also 0. And this is also plus 1. So is the charge conserved? One side it is plus 2, another side is plus 1. So it means the charge is not conserved. Whenever the charge is not conserved, it means this is not possible. Atomic scale. So this interaction from the conservation of the charge, it is not possible. If you add another proton on the right hand side, okay, you added another proton on the right hand side, and it means plus 1 and plus 1. So it become plus 2. Okay, the charge is conserved. But for an interaction, as I mentioned, charge is one of the parameter. The mass energy is another parameter. The charge might be conserved. Then we check the mass energy. Then we check the lepton number. Then we check the baryon number. Then we check the strangeness number. The strangeness number for every strange particle, whenever there's a strange particle, it is -1. And for anti-strange, it is +1. So these are all, like sometimes some interaction might happen, that charge might be conserved, lepton number might be conserved, baryon is conserved, but strangeness is not. If any one of the parameter is not fulfilled, it means this reaction is not feasible, does not happen or occur. So this is always the case. So we have to check all the interactions. We are just checking the charge here, but we can check other parameters as well. The lepton, baryon, and the strangeness number. Like if I say, let's say example, I will give about the strangeness number. These are the interaction laws, the conservation laws, which should be fulfilled. See, I just given a leave lepton and the baryon right now. Even the spin is also checked, but we leave the spin. So strangeness number, if the strange particle is there, because a neutron is a combination of up, down, down, and this is a combination of up, up, and down. So when we check the charge, it is 0. This is +1. This is -1, 0. So the net charge is 0. When we check the strangeness number, if there is a strange quark here, if there is a strange quark, the strangeness number will be -1. If there is an anti-strange quark, the strangeness number is +1. Because none of them contain a strange quark, so this strangeness is 0. This also all have strangeness 0, so the total is conserved. So it means this interaction, all the same on the left and the right hand side, so means this interaction will occur. But if we check in terms of strangeness, so if we check in terms of the strangeness, sometimes the strange particle, this is in terms of a baryon number. Here you have a charge +1, charge -1. This is an anti-proton, charge -1, kaon -1, proton +1, charge is conserved. Lepton number is, if any lepton is there, for lepton it is +1, and for anti-lepton it will be -1. But there is no lepton present, all of them, because these are baryons. Kaon is a baryon, proton is also a baryon. They all are baryons. Sorry, hadrons. Baryon is, this is a baryon, this is a meson, and collectively they are baryons. Collectively they are hadrons. So baryon, how lepton is not present? Because the this is a meson. Meson is a combination of quark and antiquark. This is a baryon. A baryon is a combination of three quarks. This is also a meson, which is a combination of quark and antiquark. And this is a baryon, which is a combination of three quarks. And collectively, they are all known as hadrons, because meson and baryon are known as hadron. So this is a charge +1, -1, -1, +1, it is conserved. When we check the lepton number, because there is no lepton present, it's a meson. Kaon is a meson. So there is not, lepton means electron, electron, neutrino, tau, tau, neutrino, muon, muon, neutrino. They are not there. So the lepton number is 0. What about the baryon number? Baryon number, for every baryon is +1 and anti-baryon is -1. So this is a meson. Meson has a 0 baryon number. This proton is having a -1, anti-proton -1. This is a meson 0 and a proton +1. So because the baryon number is not conserved, so even though the charge is conserved and a lepton number is conserved, but the baryon number is not conserved, so this interaction is not possible. So there are all parameters. It's not like only a single parameter we see. We see different parameters depending on the question. So these are the parameters we always check for conservation. If any one of them is not fulfilled, it means interaction is not possible. Is it clear? How we know the energy? These particles are accelerated by using the Large Hadron Collider. So we know what energy these particles are moving.